Hey, this is a comprehensive video tutorial about matrices and local space transformations. If you ever benefit from this video, please support my work on Patreon. This is the only way I can keep bringing you more awesome content in the future. Now sit back and enjoy. Hello my friends, today I'll give you an overview about matrices and local transforms. And I know those are very daunting words, and I myself have been struggling with matrices on the past years, but you know, I by no means any mathematician, but I just learned how to use this tool to build my 3D work. So I think now I have like a real good way of explaining that to you, and I hope that will make sense. Okay, so let's first define what is a matrix. So matrices are basically these table structures to define numbers. So for example, I am not interested in the numbers. Let's put one into everything. So I have a 3 rows by 3 columns number array. So we have a 3 by 3 matrix. So this is a 3 by 3 matrix. Alright, and these matrices can be of any sizes. So you can have like a 2 by 2 matrix, and this is 2 by 2, or you can have a 4 by 4 matrix. So 1, 2, 3, and 4 rows and 4 columns. Okay, so this is a 4 by 4 matrix, and that's just really. So why do we bother to use matrices? So in the past, some really smart guys find out that using matrices is a really good way of transforming positions in a 2D or 3D coordinate system. So for example, let's say we have this very simple triangle here, and that's made of 3 points. So we have our 3 points here, and then we want to rotate that shape into another transform. So we can just create something like this, and to rotate this triangle into this position, we are just using a matrix multiplication. So we can transform each one of these point vectors, so p1, p2, and p3. So we multiply that by a matrix, and that matrix will in turn result this transformation. And we can transform by any component, so we can rotate, translate, or scale, and the type of transformation we will get is just defined by the input numbers we have here. So different numbers will spit out different types of transformations. So be it translation, or rotation, or scaling. Okay, so this is a really efficient way of transforming things, and it also works in 3D, which is great for us. And we are going to use those to do our 3D stuff inside Houdini. Okay, so there's some small information you have to memorize, and that is, first you have one thing called identity matrix. So identity matrix. Okay, so an identity matrix will be a matrix that actually does nothing. So it's a type of matrix that it also is called a unit matrix or a neutral matrix, that if you have any shape that you multiply by this matrix, you have the exact shape without any changes. So it does nothing. It's really like multiplying any number by 1. It just outputs the input positions. All right. So this identity matrix, it comes into this structure when you have, for example, let's do a 4 by 4 identity matrix here, so I can show you what it looks like. So 0, 0, 1, and 0, and 0, 0, 0, and 1. So you see we have this diagonal row of 1 here, and whenever you see a matrix that have this, you can see that is an identity matrix. So this is a 4 by 4 identity matrix. So this is 4 by 4, but if we go and just shrink this matrix into a 3 by 3 matrix like this, you see we have the very same result. So you have this row of diagonal ones here. So this is a 3 by 3 matrix, identity matrix. Okay, so this is a neutral multiplication. Let's see like this. All right, and then we have another thing we have to memorize, that is usually 3 by 3 matrices. So let's create real quick, and I don't care about the numbers again. So let me just put X here. So don't care about numbers. So this is a 3 by 3 matrix, and this is also called rotation matrix. All right, so it's a rotation matrix. And then we have another type of matrix that is the 4 by 4 matrix. So 4 by 4 matrix. And again, I'm going to only use axis because I don't care about the numbers, just about the structure. Okay, so now we have 4 by 4 matrix, and inside of 4 by 4 matrix we can like isolate some components. So for this first array of 9 numbers here, this will define the rotation of your matrix, and then the numbers below here. So let's outline those. So the 3 numbers here below, those will define your translation. Okay, so rotation 9 numbers, translation this 3 below. Okay, and then we will not care about these numbers just for now. Just forget about those. All right. Okay, so so now we have this rotation matrix and this complete matrix with rotation and translation, and we don't care about these numbers because we are not dealing with scaling or shearing of our transforms. So let's assume this last row. Whenever we work with 4 by 4 matrices, we will assume this last row as an identity matrix. So we always assume that as 0, 0, 0, and 1. Okay, just like it is part of an identity matrix. All right. So by knowing these few concepts, we can already go into Houdini and start doing our actual local transforms. All right. So back in Houdini, and I've built myself this little gizmo geometry here, just so that we can visualize better the rotations. So you see it aligns with the default word position here, or word gizmo. And now we are going to talk about word space versus local space transforms. All right, so word space transforms is really easy. It's when you use your frame of reference is the word itself. So you use just the regular axis. And local space transformations is when you have a reference of another transform. So for example, you have this box and you rotate around the 45 degrees around the x-axis. Now you have this local space, and if you want to go up into the y-axis, you should go this way and not this way, which would be the word space. All right, so let's see how to calculate that. And so let's create real quick one. Let's rotate our gizmo here around the x-axis. Right, so for that, let me get an attribute wrangle, and that will run over points. And first of all, we are going to deal with degrees for angles, because it's easier understandable. So we're going to use degrees, but Houdini in most cases uses radians, so we have to convert those. So for example, if we want to rotate 45 degrees in the x-axis, we are going to create our variable here. So float angle in degrees. So that will be 45 degrees. But as Houdini works in radians, we have to convert that. So to convert that is real easy. We have, and let's call that angle in rad, and that we are going to use the radians function, and that will ask for an angle in degrees. So let's pass over that to the function, and we are ready to go. And then we are going to construct what we call the Euler angle. So the Euler angle is just an angle that is defined by a 3D vector. Okay, so it's like a direction, really. So now let's create a vector 3, and that's going to be called Euler angle. So we are going to use the set function that expects three axes. So will be our first angle in radians for the x-axis, and then 0 and 0. So now the fourth step, and now we're going to start converting between rotation spaces, because we have like Euler you have like quaternions, which is a most consistent and better way to compute rotations in the 3D space. And then you have the matrix 3, as I told you, it's a rotation matrix, and then you have the matrix 4, which is a complete transform matrix. So we're going to create those values and convert between one another. Right? So now you have our vector Euler angle. We can create a quaternion, which is of type vector 4. It's a vector with 4 components, and let's call that quat. And then we have to convert our Euler angle to a quaternion. And to do that, we have a function called Euler to quaternion. And that expects 2 arguments. The first one is the Euler angle we will have to convert, so Euler angle that we have above, and then the rotation order, because the rotation order matters. Alright, so we're going to use the default one, which is x, y, and z. Okay, great. So now we have the quaternion thing going on, and we are going to build again this rotation matrix out of a quaternion. So how to do that? So let's create a 3x3 matrix with this typed as matrix 3 inside Vex, and I'm going to call that a rotation matrix, or ROTM for a short version. So our 3x3 rotation matrix will be a conversion of our quaternion into a rotation matrix. That is, we can do using the QConvert function. So that will convert a quaternion, in our case is quat, into a rotation matrix, or a 3x3 matrix. And then finally we have to construct this final 4x4 matrix, and by that, to do that, we can do this. So matrix and matrix only. The matrix by default defines a 4x4 matrix, so I'm going to call that M. So that will be, we are going to create that by using this rotation matrix, which is going to go inside this pot. And then we don't care about the translation, because we are only dealing with rotations by now. So we're going to set this to 0. So Vex already has this built in for us. So if we use the set function, which has many signatures, we can use rotation 3x3 matrix to create our 4x4 matrix. And that will do just that. It will just build our rotation matrix for us from these numbers, and then for the translation part, it will just input 0, 0, and 0, so we have a neutral translation. All right, so recapitulating, we did lots of stuff here, but it's really simple. First, we created our angle in degrees, and then we converted that to radians, because that's the way Houdini likes to work. And then we create our Euler angle, which is actually a vector, a 3D vector direction. So we set our axis here, our 3 components. Then we create a quaternion out of this Euler angle by using the Euler to quaternion function and setting the rotation order. Then we transform that quaternion into a 3x3 matrix, or a rotation matrix, by using the QConvert function. And then finally we converted the 3x3 matrix into a 4x4 matrix using the set function, and then it automatically ignores anything that goes into the translation and puts 0 at every one of these values. And now that we have constructed our full transform matrix, it's just a matter of again, if you remember, multiplying the original point positions or point vectors by this matrix. So let's multiply our p, our positions, by this matrix. So times equals matrix. All right. And by doing this, you already transforming along the x-axis, and let's put that angle inside of a channel so we can easily see that in action. So rotation x, and let me get a little bit more room for the slider. Let's do 0 to 360. All right, so now you can see you are rotating around the x-axis. So now that you have built a first transform matrix, we already have this local space thing to work on. So let's say now we want to translate that into the local y-axis, which is this green axis here. So how can you do that? There's one simple concept about matrices, that to do any transformations into the local space, you have to just invert this this original matrix so that it goes back to the origin and back to the zeroed out position, and then after that you do your transforms into the word space, because you are just inverting this matrix. So you go to the word space again, do your transforms into the word space, and then apply back the original matrix to the final result. So it's just an illusion that you are working into the local space, because in reality you are just transforming that back to the original positions, do the transforming to the word space, and then applying the original transforms again, and then you have the result applied. At the final effect is like you were translating or rotating in the local space, and that works for either translation or rotations. So let's do that right now. So we have our original transform matrix, which is this M here. So let's first set this back to the origin here. So we are going to neutralize this matrix here. So to do that, we can just multiply again our points by an invert of this matrix. All right. So if we invert this matrix, we're going to set our transformation back to the word space. Right, so now we have to transform into the word space, and we are going to set to transform this y-axis up. So to do that, I'm going to first create my translation matrix, and to create my initial matrix, I'm going to create that ident matrix. If you remember, that will create like a neutral matrix. So let's create our matrix unity. So that's, again, if you don't specify this component number here, it will create by default a 4x4 matrix. So we are going to create a full matrix right from the start. So our unit matrix will be a function called ident. So that will create an identity matrix. And then we are going to, actually let's call that translate matrix, so it's easier to understand. So now we are going to translate that matrix. So we have this neat function that is called translate. Let me spell that right, translate, yeah. So this function does not return any value. So if you check the signature, it says that it's a void, which means that it doesn't return anything. So what it does, it actually translates and saves the new translation right into the argument here. So we are going to translate our matrix. So this is the matrix, and we have to set a new vector tree type for the translation. So we are going to set that. So we're going to set that to 1 in the y-axis. All right. So I have translated our initial translate matrix. So now that we have translated that, we can just apply back this original transform that we have before. So again, we just have to multiply that, because the matrix multiplication works either for vectors or for other matrices. So we can do that by multiplying our so translate matrix will be the result of this multiplied by the original M matrix, which is our original rotation matrix. And now that we have this in place, it's just a matter of setting our point rotations again. So we now multiplying by this final translate matrix. So if we do that, we now have this this gizmo transformed into the Y local axis. So just to visualize that better, we can create a channel for this. So channel, let's say Y translate, and let's apply that. So you see we can translate into the Y-axis, into the local Y-axis, and it also computes for any rotation. So let's say we want, instead of 45, I want don't know, 20 degrees, and it already is working at the local space. So now that you have that, we can just stack this matrices multiplication on top of one another, so we are getting local transforms. So for example, let's say that from this current position and rotation, we want to rotate around this this z-axis. So how can you do that? Then again, first step is to get our matrix or invert matrix, so that this object is back at the origin. So let's do again, let's invert our last matrix value here, and then we have to recreate all this stuff here. So now we are going to rotate around the z-axis. So let me create an float angle here. So angle in degree for the z-axis will be, let's say, 30 degrees. Now we have to create the radians from that. So angle in radians for z will be radians of this variable. Now we have to convert that into or to create our Euler angle from this rotation. So let's create that as a vector 3. So vector Euler angle for z will be set vector. So x and y will be 0, and z will be our angle in radians. Okay, so now we have to create a quaternion from this Euler angle. So to create that, remember, is a vector 4 type of variable, which is a quaternion, and I'm going to call that quaternion z, and that will be an Euler 2 quaternion. And we are going to use the Euler in z, Euler angle for z, and also remember we need the rotation order, which are going to use the default one, x, y, and z. Right. Now we have to transform the quaternion again into a rotation matrix, which is a 3 by 3 matrix. So matrix 3, let's call that rotation matrix for the z axis. So that will be a quaternion convert function of the quat z variable. And now we have to build our final matrix, or 4 by 4 matrix out of that. So matrix, and you just don't need to specify that it's a 4 by 4, it's just by default is a 4 by 4 matrix. So let me call that M for the z rotation, and that will be a set function of the rotation matrix for the z axis. Okay, so now we are left out with a 4 by 4 matrix with our zeroed out translation. All right, so now that we have that, again we have to multiply that back to the original transform matrix, so that we just undo this invert sign here. So our mz will be equal, or times equal or translate matrix, so our previous transforms. And then finally we just apply that back again to the points. So points will be translated with the matrix of the z rotation again, and sure enough, now you have this rotation working. And just to prove that, let's again create a channel for that, and let's call that rotation and Z. And I'm get again a little bit more room for my sliders, so 360. And now you can check, you can rotate along the Z-axis. All right, so we can rotate along the Z-axis, and we can translate around the Y-axis. So we are doing three ordered operations. First, we are rotating in the X axis here, and then we are translating local into the Y axis, and then we are rotating local into the Z axis. All right, and we can do that so on and so forth for many iterations. So that's the way you can calculate and set your local transforms using Vex and a little bit of math and just a basic understanding on matrices. Alright, so now that we have all this understanding, let's create something more modular. So let's again create an attribute triangle, and that I'm going to call rotate in local space. So here we are going to do the same thing. So let's start with our angles, but now we are going to build out 3 angles. So for that we are going to use channels. So float angle X will be a new channel for rotation X, and let's do the same for the other axis. So X, Y, and Z, Y and Z. Now we're going to create the radians for that angles. So float angle rad X will be radians of angle X. Again, let's do that for Y and Z, Y and Z. And now we can start converting and creating our final stuff here. So let's first create our Euler angle. So vector 3, Euler will be set, and we're going to use each of the angle in radians. So X, Y, and Z. And now we can create a quaternion from that. So vector 4 for quaternion. What will be an Euler 2 quaternion function that expects an Euler angles and the rotation order, which we're going to use the default one, X, Y, and Z. And now let's build a rotation matrix out of the quaternion rotation. So matrix 3, M3 will be the quaternion convert of these quaternion rotations. And finally our 4x4 matrix, M will be the set of rotation matrix. All right. So now we have our created our transformation frame here, and now we can check. So we're going to persist this rotation into the geometry as a detail attribute. So we need to check if it already exists. And if it does, we are going to do that inverse multiplication thing before we set that to the points. Okay, so if has detail attribute, the input geometry, and the attribute name I'm going to call that X form. So if it has that, then we are going to invert that before applying the multiplication. So matrix input X form will be the detail attribute of the input geometry and the X form attribute, and we just need to first multiply our points back to the invert of this input X form, and then we need to multiply our build matrix with this also input X form, and then we set the back to points. So P times equals M. All right. Actually, let's do that right after the detail because we need to do that anyway. And as a final step, let's also set our detail attribute. So we are going to update the input X forms. All right. So let's set that on the input geometry on the X form attribute, and the value will be M for the updated matrix. All right. So let's create our input sliders here, and again let me get some more room, so from 0 to 360. And now we can start working into the local spaces. So let's rotate again 45 degrees in X, and if we just duplicate this node, we can do additional transformations. So I'm going to transform 45 degrees into the z-axis, so we just, or 90 degrees into the z-axis, and now I'm going to translate to rotate into the y-axis. So it's just copying and pasting, and let's zero that, and let's rotate around this axis. So you see, you can create like stack rotations into the local axis, right? So yeah, so now we have this. Let's check the z-axis again. Yeah, okay. Yeah, so you see it's working. And now, just like the rotation node, we can do a translation. So let's do again with the translation into local space. So again, attribute wrangle, and let me call that translate in local space. So it would be very similar. So first thing is, let's construct our transformation matrix. So for the translation, it's easier. We just have to create an ident matrix. So matrix ident. So let's call that M, just for compatibility. So matrix M will be an ident matrix. And then we need to translate that. So translate, and this translate function, it doesn't have any outputs. It just translates the input matrix itself by some vector. So our vector will be again, let me create the channels here. So float and translate x will be a channel translate x, and let's do that for the other axis. Okay, and now we are going to set this vector with the 3 axis values here. Sorry, and that's z, right? And we have to now that you have this matrix created, we have to check if it has this attribute here. So let's just copy and paste that, and if it has the xFrom attribute, it will just copy that to memory, and then we to invert the transforms, just so that it get back to the word space, to the origin. And then we are going to translate the M to multiply this M matrix with the input xFrom, and then finally set that again to points and update the attribute. So it's already working, or it should, and that's because we have a typo here. Okay, so now we want to translate into local space. So if you see, for example, let's translate into this y-axis. So we can see it is working, and z-axis it is working. So let's give it some different rotations. So 45 again, and let's transform into the y-axis or on the z-axis, and again you can just stack those transformations. So let's now rotate around the y-axis here, and now let's translate into the z-axis once again, and you see it just works. So you can stack multiple of these nodes. So as soon as you have the first input matrix set, you can just carry on by persisting the attribute at the geometry detail as a detail attribute, and you can just work local as much as you like. Okay, so yeah, so that's it for these transforms, and now we are going to see how to create how to build a frame out of a geometry, because oftentimes you just receive, so let's say you received a model that is already transformed, like for example you have a model that is like this, and you just you need to build a transform frame from this model. So we don't have any informations about the matrices here, so we don't have nothing. It's just a model that we received. So how can we build these transform matrices from a primitive? So let's say from this polygon. So that's what we're going to see next. Alright, so how can we create a polyframe from this from any primitives of this geometry? So let's go back to Photoshop again. Let me get some background information. So when you have this polygon mesh, we let's say we have selected any primitive to become our polyframe reference. So you have, for example, this grid here that is part of a cube. So let me do that very roughly, and forgive my drawing skills here. Right, so we have this cube, and we have decided that this primitive will be our reference frame to build our matrix. So we are only actually interested in just only two edges. So for example, we are going to pick two random edges, for example this one and this one, and that's all we need to build a reference frame from this, because that two edges will define a triangle. And if we have like one line here and one line here, that defines a plane. So with this plane here, we can create what we call a cross product, with which is basically, and let me get another color to draw here. So a cross product will basically create a 9-degree angle between a plane you define, all right, which also happens to be the norm of the triangle. Okay, so again, let's say we have this triangle over here, and you have for example, you have this this edge and this edge. So you have defined a plane here. So the normal of this the cross product between these two vectors, so vector A and vector B, will be this line that is fully perpendicular to this plane, over here. All right, so this is the cross product, and we are going to build our matrix by using just these two edges. So and the center of the matrix can be at the polygon itself, or it can be at the centroid of the input object. We can see that later on. All right, so with this we are going to work with the concept of half edges, which Houdini let me show that for you. So this is an excerpt of the Houdini documentation. So half edges is, as you can see, is something it creates for every primitive. So you have one edge going from one point to another, and it's like each edge has like two parts that have a certain endpoint. So for example, this edge goes from this point 0 to this point 1 in this direction, and then for this other primitive it goes the other direction. So this starts at 1 and goes to 0. All right, so this is what Houdini calls an half edge. All right, so we are only interested into one of those, and then Houdini has a method to get the next connected edges to this. All right, so for example, we can get this one, and by getting two edges we already define a plane where we can run the cross product functions to have our three rotation axes. All right, so let's do that in Houdini. Okay, so here we have our box, and let's do again our attribute wrangle. But now it's going to run at the detail because we just actually we will only need to set up one matrix. so we just don't need to run over points, right? So let's turn on our primitive numbers here, and I'm going to use the primitive number 5 to find for all the edges, which will then construct our plane, and then in turn will we get access to or actually to build our rotation axis. So first thing is, let's define which primitive number we're going to use as a reference frame. So int prim number will be 5 in this case, and now we're going to start working with the edges. So first thing is, let's get our edge here. So there's one thing called prim hedges, yeah, prim hedge, and this will return an integer value that will return the index of the primitive half edge. So we're going to, let's check the spelling here real quick. So it needs a geometry and a primitive number. So geometry is the input geometry itself, and the primitive number we have defined over here. So we have this, right? So for this primitive edge, we can have its next connected edge. So for this, we can call this function hedge next. So hedge next will get for this geometry the next half edge that is connected to the one before. So actually, let's create our variables here. So this will be the edge A, and this will be our edge B. Right, so we need the next half edge that is closer to edge A. Right, so now you have and the edge it selects because each primitive has many edges, but in this case we don't know, it's actually arbitrary. If you check this function, we can see that it states that so the number of an arbitrary half edge, so it just selects the first one it finds, I believe. So as we are not interested in just we could also specify which edge we are using for the operation, but in this case I just want any edge that's connected to this primitive. All right, so this just ensures it gets any available edge, and then it also ensures again that you have the next edge that is connected to this one, because for example if it selects this edge here, this next edge will either select this one or this one, but not this one. All right, so it doesn't select parallel edges. So yeah, once you have that, we have this concept of start and end points of an edge, because as Houdini states, it has the half edge, it has a start and end point. So for each polygon it can vary. All right, even though they belong to the same edge. So the half edges are something that is it has also this thing with the start and end points, right? So and it also is going to give us point indices. So let's call that edge A start or P1 rather, and that's going to be the half edge start source point. Yeah, so the source point of this half edge, and let's check the spelling again. So it needs the geometry and the edge, so we're going to use the input geometry and edge A. So you get the first point connected to edge A, and let's get the second point. So edge A P2, which will be instead of source point is the destination point, right? So we have the first and last points, and let's do the same for the edge B. So we have edge B P1, edge B P2, edge B, and edge B. All right, so now we have the 4 point indices, and then we have to finally get the positions from these points, because remember this function is returning only point indices. So to have the positions, it's just a matter of having so vector. So let's call that A, so edge A and 1, so edge A and point 1. so that will be the point function for the first input geometry. The attribute name will be position, so we are interested in the position. And let's check what else we need. And the point number, of course, yeah. So we need the geometry and the attribute and the point index. Those 4 points here. So edge A and B and points 1 and 2. So let's start with the first point. And next let's do that for all of them. So A1 and A2. So B1 and B2. So this is point 2, 2 and edge B, edge B. Alright, so we have our 4 positions here, and it's a typo. Alright, and now we need to start creating our vectors. So our first vector, which will define our x-axis, so let's call that vector x. So that will be A2, so the second point, minus A1. And I like to do in this order because the order of this operation will define to which direction this vector is going to point to. So for example, if you have let's say we have here vectors okay, so we have vector A is a point here and vector B is a point here, and if you do A minus B you have this. If you do B minus A you have this. Alright, so the order of the operation defines where the vector is going to point to. So I like to do, for example, if I have A and B, I like to do B minus A because this is the first number and this is the second number, and my arrow will be pointing from the lower to the higher number. Alright, so I just like to do that way. And we also have to pay attention to the size of this vector, because we are not going to we are not interested in the size of the vector, but rather in the direction. So we are going to normalize that so that you have a unit vector. And we are going to now we are going to do one thing. So for the temporary vector, we just create like so this will be vector x. Now we're creating a temporary vector, so like vector TMP, and that's going to be the other edge. So we're going to do B2 minus B1, and that is temporary because let's say we have a polygon that is like this, for example. So let's say you have this polygon and we have 2 edges that should be this one and then this one. Alright, so we are defining this direction as being our x-axis, so this should be x-axis, but we don't want this to be our z-axis because we want that to be something like this, or something like in a straight 90 degrees angle. Right, so we are going to compute the second angle also with cross products. So just for the moment, let's define that as a temporary vector, so that you can create our first y-axis. So temporary vector, that will be B2 minus B1. So our vector y will be the cross product between both of these ones. So this is the cross product between x and the temporary vector. And our z-axis now will be in turn another cross product that's going to be between the y-axis and the x-axis. Or actually, yeah, we have to test the order here. Alright, so now we have a perfectly built rotation frame. Alright, so that's our rotation frame, and now that you have this, it's just a matter of reconstructing, and sorry, this is not x, this is z, and now that's a matter of constructing our base base matrix. And just for the moment, let's define. So here we are, up until now we are defining our rotation component of the matrix, and now let's define our translation component. And just for the moment, let's say that our vector center will be the get bbox center of the input geometry, right? So we're going to construct this matrix and position that to the center of this object. Alright, so let's create our matrix now. So we have to create this matrix, 4x4 matrix from vectors. So for this we can use another signature of the set function. So let's create that matrix M, and that would be set, and we can set this matrix with 4 vectors. So X, Y, and Z, that will define the rotations, and the last vector will define the translation. So we have everything in place, so you just have to set to X, Y, and Z, and also the center vector. And now, as a last step, as you remember, I have told you earlier that we are going to assume that in a 4x4 matrix. So let's do that real quick. So you have 4x4 items. We are not interested in those in this column over here. So we always treat this as it was part of an identity matrix. So we always leave that at 0, 0, 0, and 1. But in this case, the way Houdini creates this thing here, we can visualize that if we input that into an attribute. Let's say that there's a 4x4 matrix attribute that we are going to store the detail. Let's call that xform, and that will be our M value. So if you check on the spreadsheet, you see at every fourth row here, so it's like it's creating by row. So row 0, column 0, row 0, column 1, column 2, and column 3. So this one here should be this value here, and another 4 numbers, there's another one here, which is this one, and another 4, there's another one, which is this one, and so on and so forth. So it is creating with ones inside of this 0, 0, 0, and 1 only on the last one. So we're going to correct that by using a function called setComp, which sets the component of a matrix. So we can use this setComp, and setComp works by working on a defined matrix, which in our case is M, and then we can set the value. So the value of this component will be 0, and the row where it operates will be the row number 0, and the column will be column number 3. All right, so it's like we are working. So if we break down this thing as an array, this should be something like this is the row 0, the row 1, the row 2, and the row 3, and this is the column 0, 1, 2, and 3. So we want to modify only those 3 numbers. This we're going to leave at 1, but these ones have to be 0. So the positions we are going to change is the 0, 3, so row 0, so this is row, and this is column, so row 0, column 3, so 0 and 3. We're going to change the row 1 and 3, row 1, column 3, and finally the row 2 and column 3, so 2 and 3. So we're going to change the components of these items. So again, setComp for the M matrix, the value will be 0 for the row 0 and column 3, and let's do for the other 2 rows, so row 1 and row 2. Alright, so now that we have constructed our whole matrix, we can just set that. So you can see it already puts 0 at these numbers, and we have 1 at the last one, which is exactly what we want. So now that we have this, we can start working into local space, because we already defined this this input transform matrix. So let's just, as a last step, instead of yeah, we actually already saved it in an X form, so it's the same name. So let's just use our previous nodes here. So let's get our transform in local space, or translate, and let's translate using the y-axis, for example. So you can see it's already doing the translation in the y-axis. We just have to swap the components here, because we are getting the y-axis to be upside down. So we just change the cross product here from xy to, or from yx to x and y. This way we are flipping the axis, and now we get the right transforms. Actually, it's not that one. We had to flip between these ones, so PMP and X. Yeah, now it's good. So you see, you have the Y axis, and you can translate on the X axis and the Z axis, and it also works for rotations too. So let's see if you can rotate around the Y axis, and it rotates. All right. So now that we built this reference frame and in position at this primitive number 5, we can do that for primitive number 0, for example. So let's put that reference frame at primitive number 0. And now if you rotate around the x-axis, the x-axis, or actually the y-axis, is pointing along this direction. So we can rotate around that axis too. And for example, if you translate, then it goes to that direction. So that is our new y-axis, right? So now with this other thing you can do, let's go back to the primitive number 5. We can start constraining objects to this object. So for example, so let's rename things. So this builds a polyframe, and now I want to create another box, and let's make that 0.2 in size, and I want to attribute wrangle. I want to transform this object to this input matrix. How can you do that? So remember, it's just a matter of multiplicating points to matrices. So if you run that over points, we can just multiply our point position by this transform attribute we have set here. So let's multiply that by the detail attribute of the first input geometry, and the name is xform. So let's visualize that. And actually is not the geometry number 0, is the geometry number 1, it's the input number 1. And this is giving me errors because we have to explicitly tell Houdini that this is a matrix for type of variable. So we just have to cast that to a matrix. And now you can see it just creates like a constraint, a position constraint, and position and rotation constraints to this box. So we can now go and start rotating, and you see it's just going to stay in synchronization with the rotations. So another thing we can do is, instead of setting because remember we have two components, we have built the rotation component and the translation component, and the center of this matrix we have set to the centroid of the input geometry. But we could always do that to the centroid of the primitive number itself. So let's do that right now, just as an alternative. Instead of getting bound box center, we're going to search for the primitive attribute on the input geometry, and the attribute will be P for position, and the primitive number will be this first primitive number we defined over here. So that should give me center. Let's see what's going on, and let's check. And yeah, it's actually working. So you see now you can position that to the center of our primitive. So you have a constraint to your primitives. So let's say our box is just above the ground by the half of this scale, so divide that by 2 and you get that right over the ground. So if we position that using our new matrix, we have that actually fully aligned to our initial geometry, and it's again, it just have to rotate that and it also will work, so it just sticks to that position. All right, and then it's just a matter of switching input geometries. So let's make a torus, and just for easiness, let's also put that into a channel. So channel integer, and let's call that prim number. So we can easily select what primitive we are going to use here. So now you see it's a very quick way of constraining objects to primitives. So let's switch our geometry and let's just copy those initial values here. So paste values and copy parameter and paste values. So let's switch that to a torus. And you see we can find other primitive numbers, and it will just find the center of this primitive and just stick to that center. So, and you can then rotate and do whatever. Alright, so with this I think I covered a big chunk of things about matrices and local spaces and how to use that to have a working solution. So, and I hope I clarified some of our questions about it, and let me know what you think in the comments if you have any questions. And again, for those that subscribe to my Patreon, these examples will be available and fully commented with HDAs ready to be used in your project. Okay, so thank you for watching, and we see you in the next video. Bye bye.